We're now going to discuss the second type of SN2 reaction, the unimolecular nucleophilic substitution, or SN1 reaction. The thing that distinguishes the SN1 from the SN2 is the different mechanism. The SN1 reaction goes by a multi-step mechanism. In the first step of the SN1 mechanism, the leaving group breaks its bond to the substrate carbon. This leaves that carbon with only 3 bonds and a positive formal charge. We'd call this type of species a carbocation, cation being the term for a positively charged ion. Of course, we would also have a leaving group byproduct that, again, normally we just ignore. In the second step, the nucleophile makes a bond to the carbocation carbon. So it takes this pair of electrons, it puts it into the empty space around the carbocation, which currently has an incomplete octet, and it forms a bond. Now, what we see is that there are 2 different types of nucleophiles that make a difference in how this mechanism proceeds. The most typical type of nucleophile that we see in an SN1 reaction will be a neutral nucleophile with a hydrogen attached to the nucleophilic carbon. In that case, as written on this line, when the nucleophile makes a bond to that carbon, it should then gain a positive formal charge. It's going to want to lose that formal charge, so we're going to need another step in order to do that. However, if instead the nucleophile has a negative charge already, then when it makes a bond to the positive carbocation, the product is neutral, and we would stop there. So we have to understand a little bit about what our nucleophile is and what it's doing in order to decide whether we need to add another step to this mechanism. The last step then would only occur when the nucleophile gains a positive charge. What we would want to do is make it neutral. And one strategy that can be used by the system is to have a base make a bond to a hydrogen on the nucleophile and then release the pair of electrons from the other side of the hydrogen to go onto the nucleophile as a lone pair. This would then cause the nucleophile to effectively gain 1 more electron and go from being positive to being neutral. Now, we wrote that mechanism as 3 separate reactions, and in fact, if you look, what we did was we took the product of the first elementary reaction and we moved it down to make it the reactant of the second elementary reaction. And then in the case where we moved to a third one, we took the product of that and moved it to the reactant of the third reaction. These intermediate products then, these products that occur during these elementary reactions but don't appear in the overall observed reaction, these are intermediates. So for example, the carbocation is an intermediate in the SN1 reaction. It's actually quite an important intermediate. We do, however, have the option of writing this reaction all the way on one line. So what we would do in that case is we would start with our first reactant, we would draw our arrow, we would have our product of the first reaction, and rather than writing a second line and recopying that product, we would just draw an arrow extending from that product with whatever reagents over the arrow to the next product, and then again draw an arrow extending from that product to the final product. This is called a one-line mechanism. It should be noted, however, that in this mechanism, each arrow represents an elementary reaction. We're now going to look at the energy profile and rate law for the SN1 reaction. The SN1 reaction has 2 or sometimes 3 elementary reactions. We're going to look at the example where it would have a neutral nucleophile and it would therefore have a 3rd elementary reaction. What we see then is, because there are 3 elementary reactions, there are 3 different transition states, because each elementary reaction should have its own transition state, which means that we have 3 humps in our energy profile. Generally, it's accepted that the energy profile for the first elementary reaction should go up to a very high energy transition state and come down to a carbocation intermediate, but that intermediate should be higher in potential energy than the initial reactant. So it would be an endothermic reaction. Then we would see that as we form a bond to that carbocation, the potential energy should go down, and then in the case where we have a 3rd reaction step, because we are making that intermediate neutral after having being positively charged, the potential energy goes down again. In most SN1 reactions, the rate determining step will be the first step. That transition state usually has the highest energy. So, if we look at our rate law then, the rate should be the rate constant times the concentration of the substrate. Because if you'll notice, in this first step, there is no nucleophile participating. It's just the substrate breaking apart into the carbocation. So, the SN1 then is a unimolecular reaction because it has only 1 molecule in its rate law, and it's first order. This then allows us to just use reaction kinetics to determine whether a given reaction is going by the SN1 or the SN2 reaction. If it's following the SN1 reaction, then changing the concentration of the nucleophile should have no effect on the rate of the reaction. Whereas if it's following the SN2, if we change the concentration of the nucleophile, the rate of the reaction should change proportionally. Carbocations are extremely important intermediates in chemical reactions. We first encountered them here in the SN1 reaction, but we are going to see them in a wide variety of other reactions. It's going to become very useful, therefore, to understand a little bit about their specific properties. If we look at a carbocation then, we can see that the carbocation would have a steric number of 3, which would make it trigonal planar. In order to be trigonal planar, it would be sp2 hybridized at the central carbon. If we then sort of sketch a picture of how the sp2 hybridized molecule looks in 3 dimensions, we can see that the 3 groups on the ends of the bonds would be arranged in the trigonal planar arrangement, 120 degrees apart, all flat in a plane. And then there would be an empty p orbital with no electrons in it, perpendicular to that plane. Now, if we look at carbocations, carbocations fundamentally lack electrons. If you have a positive charge, you have fewer electrons than you need to balance out all of the positive charges in your nucleophile. In our nuclei. We have a term that we use for that. We say that they are electron deficient. Now, one of the things then about electron deficient groups is that if we change their structures a little bit, we can change their potential energy. Specifically, if we change the carbon groups or change the groups attached to the central carbon and replace them with groups that donate electrons, that will help stabilize that central carbon. It turns out that what we have discovered is that if we compare a carbon group to a hydrogen, carbon groups are more capable of donating electrons. So therefore, as we increase the number of carbon groups attached to the central carbon of the carbocation, the carbocation itself will become more stable. Its potential energy will be reduced. So therefore, we can sort of summarize this carbocation stability by using our previous classifications of carbons. What we see is that a methyl carbocation has 0 carbon groups, and it turns out to be extremely unstable to the extent that under normal circumstances it does not form. Primary carbocations would have 1 hydrogen replaced by a carbon group. It turns out that these carbocations can be formed, but they rearrange almost immediately, which is another aspect of carbocations that we're going to discuss later. Secondary carbocations with 2 carbon groups are more stable than methyl or primary, and tertiary carbocations should be the most stable carbocations of the ones that we are currently considering. Now, when we looked at the SN2 reaction, we saw that it was stereospecific. If we used one configuration of the reactant substrate, we would get a specific configuration of the product. It turns out that because the SN1 goes through a carbocation, it has a completely different stereochemical course. So we're going to have a rule here, which I probably should have put in bold. When a stereocenter is formed at a carbon that is planar, it's planar either in the reactant or in the intermediates, then both configurations of that stereocenter will be formed. So if we look, carbocations are planar. So the nucleophile could make a bond to either the top face of the carbocation or the bottom face of the carbocation with an equal probability. Therefore, the SN1 reaction results in a 50-50 mixture of configurations at the reacting carbon. So if we look, we start with this stereoisomer of our substrate. We're going to assume that we would have 100% of this configuration, where the chloride leaving group is on a wedge. We then treat it with sodium iodide in an SN1-like reaction. In that case, what we would see is that about half the time, the iodide would attach on the opposite side from where the chlorine was, but in the other half of the time, it would actually attach in the exact same place as where the chlorine was. So, attaching on the opposite side is called inversion, and this is the outcome that we see in SN2, 100%. In the SN1, we have a second outcome called retention. And we generally expect to get about a 50-50 mixture of these. If we look at this using three-dimensional pictures, we can see what's happening. The chlorine atom breaks off of the substrate. When it does that, this pair of electrons right here is no longer available to push these 3 other groups down by VSEPR. So these groups move up into a planar configuration, and we have this p orbital above and below. When the nucleophile then comes in to make a bond, remember that bonds are formed by the overlap of orbitals. So it has an orbital, for example, on the I-, it would be an sp3 hybridized orbital. that orbital would come in, it would overlap with this part of the p orbital, the pair of electrons would flow in, the p orbital would rehybridize to an sp3 orbital, these would be pushed away, they would be pushed down, and we would get this stereoisomer. In contrast, if we do the same thing but come from the opposite face where we interact with the other part, the other lobe of the p orbital, then our bond would be formed on the bottom face and these three groups would be pushed up. So that results in these two mirror image configurations. Now, we have to be careful. If the reacting carbon is the only stereocenter, then what's going to happen is we are going to get a 50-50 mixture of enantiomers. Actually, it should say chirality center there. So here's the chlorine. It's on a wedge. Our nucleophile that I'm going to use, for example, is water. That's a neutral nucleophile, so it's nucleophile H. So the actual thing that ends up attached after we remove the H would be hydroxyl, OH. If we do this, we should get 50% retention where the chlorine's on a wedge and the nucleophile OH is on a wedge, and 50% inversion. And it turns out if we make mirror images and stuff like that, we would end up recognizing that these are enantiomers. However, if there are other stereocenters that don't react, then the product will be diastereomers. So, doing a very similar reaction to the one above, but instead of having two methyl groups here, having only one methyl group, that makes this a chirality center. However, this chirality center does not react. No bonds are broken, no bonds are formed to these carbons. Only here where the leaving group is attached. So again, 50% of the time the OH is on a wedge, just like the chlorine, and 50% of the time the OH is on a dash, the opposite or the inversion of the chlorine. But this other chirality center does not change. So these are no longer enantiomers. These are diastereomers. One chirality center has opposite configuration. The other one is the same in both molecules. Another special characteristic of carbocations is that they can rearrange their skeletons to become more stable. Rearrangement changes the connectivity of the carbon skeleton. There are two types of rearrangements. The first type is called a hydride shift, in which a hydrogen plus a pair of electrons, which if we look at it by itself is this species, hydrogen minus, or hydride. That hydrogen moves to a nearby carbocation carbon. The pair of electrons moves, it brings the hydrogen with it, and so what has happened now is that the hydride is attached to a different carbon, and then the original carbon has an empty space or an incomplete octet, and it becomes a new carbocation. It's important to note that in this shift, what is moving is the electrons, not the carbocation. So we don't draw an arrow showing the carbocation moving, we draw an arrow showing the bond containing the electrons moving. Starts on the bond, points to the carbocation. A similar kind of thing can also occur with carbon groups. Same thing. Carbon group here has a bond. The bond moves over, so we get that carbon group attached to a different carbon, and then the original carbon has an incomplete octet and is a carbocation. In general, with regard to carbon groups, smaller groups are better at moving. However, I just want to mention briefly that the phenyl group is exceptionally good at moving, although hydrogen is even better than phenyl. So this is going to present us a problem. So if we look at this proposed reaction here, we have a substrate. Here is our substrate carbon with the leaving group attached. We treat it with a nucleophile. In this case, I used water to really emphasize an SN1 mechanism, which would have a carbocation. What we would see, very interestingly, is we would see a mixture of products. We would get this product where the nucleophile replaced the leaving group directly on this carbon right here. But we would also see a product where the nucleophile has replaced or been attached in a completely different carbon. So there's a couple things about this. First of all, this sort of highlights one of the differences between equation writing in organic chemistry and equation writing in general chemistry. Most of the simple ionic type reactions that you study in general chemistry have very clearly defined products, and they occur, or the products appear in a one-to-one or at least a fixed stoichiometry to the reactants. In organic reactions, what we have is a situation like this. We might start with 1 mole of this reactant, but at the end, we would have fewer than 1 mole of this product plus fewer than 1 mole of that product. Together they would add up to 1 mole, but each one would not be 1 mole. Instead, often what we do is we write percentages. Such and such percentage of this and such percentage of that. The problem with this then is, what would we put for coefficients? Would we put fractional coefficients? It just doesn't make sense. So in fact, actually, we often don't really balance the products in organic chemistry reactions. We typically just sort of set up the reactants and reagents in a balance. But when we do actual reactions in lab, we'll see that we often don't even use those stoichiometrically. So it's just a very different way of thinking about reactions from what we did in general chemistry. Now, why do we get these two products? Well, here's what happens. The leaving group leaves. That creates a carbocation right here. Now, the nucleophile could plug into that carbocation. It just requires a collision between a nucleophile molecule and the carbocation ion. And then it would be deprotonated in a separate step, which I'm not drawing. But essentially, if the nucleophile reacts with this carbocation, we get this product. In contrast, the carbocation has the opportunity to rearrange. The reason why it would want to rearrange is that this is a secondary carbocation. If this hydrogen were to shift over, that secondary atom would no longer be a carbocation. Instead, this atom, which is a tertiary carbon, would be the carbocation. So this carbocation here would be more stable than our initially formed carbocation. That's the incentive for rearranging. If, however, we form this tertiary carbocation, then the nucleophile would react right there on the tertiary carbon, and we would get this product. So, one of the other issues then that organic chemists face is, how do we write this reaction? How do we communicate this reaction? And how do we plan with this reaction? So for example, if I were trying to make this molecule, and I said, why don't I take this reactant and this product, and it should make this molecule. That's absolutely true. But I would also make this molecule. And in fact, in many cases, the rearranged molecule would be formed in larger quantities than our desired molecule. So, for the purposes of our class, what we are going to do is we are going to assume that any carbocation that can rearrange to become more stable will rearrange, and that the preferred product will be from the rearranged carbocation. So we would write this product. And in fact, we will not write non-preferred products. Again, this is just a choice that we're making. We know that in our real reaction, we would get a mixture of these. However, it turns out also that we have no way of predicting what the composition of that mixture would be. That composition could be affected by a variety of factors: the concentration, the temperature, the solvent, the length of time. There's a whole bunch of things. And so we might run this identical reaction 3 different times and get 3 different distributions or relative percentages of products. So that's why we don't treat these reactions so heavily quantitatively in our theory. The only way that we can really determine what the percentages are is empirically in the laboratory. That then concludes our discussion of the nucleophilic substitution reactions. In the next chapter, we're going to talk about elimination reactions and also put elimination reactions together with SN reactions to get a larger picture.